Good morning. My name is Andrea Porfiri Dalcin. I'm a PhD student at Politecnico di Milano, and today I'm going to present multi-body self-calibration, also on behalf of Giacomo Boracchi and Luca Magri, who also work at Politecnico di Milano. Self-calibration is the problem of estimating the intrinsic parameters of a camera, and this task is fundamental for the problem of structure from motion, which is the task of recovering the 3D structure and the camera motion of a scene. Structure from motion operates on static environments, and dynamic objects, so rigidly moving objects, are treated as outliers. Moving objects can be detrimental to performance due to the fact that they generate occlusions in the static environment. So our question is, can we exploit the multiple objects in order to improve the results of self-calibration? Self-calibration is possible because multi-view relations provide more constraints than those needed to compute rigid displacements. If we take two views, for instance, we can compute a fundamental matrix F, which, due to the fact that its determinant is equal to 0, has 7 degrees of freedom. From a fundamental matrix, we can compute a rototranslation which has 5 degrees of freedom. This means that each fundamental matrix can be used to constrain the internal camera parameters of a camera due to the fact that there are two constraints that can be imposed on the matrix K of camera parameters. Traditional self-calibration, just in structure from motion, assumes that scenes are static and treats motions as outliers. But more constraints derived from more fundamental matrices lead to better estimates of the internal camera parameters. Also, the fact that self-calibration with multiple bodies relies on multiple fundamental matrices limits the chances of motions that are poorly constrained. Finally, an advantage is also that we avoid most of the times degenerate solutions due to the fact that it's unlikely that most motions are parallel to the optical axis of the camera. So our goal here is to design a novel multi-body self-calibration pipeline that takes advantage of all the moving objects in the scene in order to better constrain the camera parameters. This is the proposed pipeline, which takes as input a set of images, segments the motions in the images to compute fundamental matrices and tentative focal length values, and therefore uses both fundamental matrices and focal lengths to initialize the parameters of a camera, compute a robust initial estimate of the focal length, and then drive an optimization problem in order to compute refined intrinsic parameters. Starting from motion segmentation, we take two input images at a time, II and IJ, and extract key points in these images and use T-linkage coupled with the 6-point algorithm to obtain segmented key points depending on their motion, and a set of fundamental matrices, one for each motion, and tentative focal lengths, one for each motion. T-linkage is a multi-model fitting algorithm that uses a hypothesize and clusterize strategy. We augment T-linkage with the 6-point algorithm to obtain not just fundamental matrices from the multiple motions, but also tentative focal length values. These are used in order to derive ranges of likely focal lengths for our scene. So for a subset of image pair, we obtain a set of fundamental matrices, one for each motion, which provide constraints on the camera intrinsics, and also a set H of focal lengths that provide educated guesses for the initialization of parameters of the camera. Next, we try to find optimal initial parameters for our camera in order to start an optimization procedure that is nonlinear and thus requires an initial estimate of the solution. So given the fundamental matrix F and the aspect ratio which is known from the input images and an estimate of the principal point at the center of the input images, we use the focal length guesses Fj in order to compute a semi-calibrated fundamental matrix G using Storm's equations. So this semi-calibrated fundamental matrix can be used in order to rewrite the Krupa equations in terms of the singular value decomposition of G. So every semi-calibrated fundamental matrix returns an estimate of the focal length, of the true focal length of the camera. So for every fundamental matrix Fk, we try all the focal lengths Fj in our tentative set H, and we get a solution F star to the Sturm's equation using Fj as initial guess. So the solution F star is used as a vote to cast a vote. And finally, a kernel density estimation step is used to estimate the probability density function of F. So for our robust initialization, we take the peak of phi of F in order to drive the subsequent nonlinear optimization problem. In the figure on the right, you can see that tentative focal lengths concentrate around the true solution, which is in the middle of the plot of the histogram, and therefore we use a Gaussian kernel for our kernel density estimator in order to remove the effect of outliers and mitigate the noise. The probability density function of the focal length estimated using the KDE is used to drive a multi-start nonlinear optimization scheme that refines camera parameters in order to obtain accurate results. We use a Levenberg-Marquardt scheme that randomly samples the initial seed from the distribution phi of F and iterates in order to find the best solution. The cost function for this minimization problem is defined by the Mendonça and Cipolla cost function, which encourages the essential matrices computed from the camera parameters and the fundamental matrices to have equal singular values. Finally, we show experimental results that demonstrate that our multi-body self-calibration method properly exploits the multiple objects in a scene to improve the results and the accuracy of self-calibration. For starters, we decouple the evaluation of our robust initialization and our optimization scheme in order to evaluate the benefits of both steps of the pipeline. In this plots, you can see the probability density functions estimated using our kernel density estimator and the peaks of the distribution. You can see a comparison of the focal length estimated by competing methods in green and red and our method in blue. You can see that our method consistently outperforms the others in both static datasets on the left and dynamic datasets on the right. You can also see that dynamic datasets are usually noisier due to the fact that some motions are not well represented by the sift key points we use to extract information. This is a box plot of the error, the relative error of on the focal length produced by our method with respect to the ground truth focal length. And again, our method is displayed in blue and shows better performance compared to competing methods. Finally, we evaluate our robust initialization and our optimization step jointly in order to provide a better understanding of the full proposed self-calibration pipeline. We tested our pipeline on both its single body and multi-body configuration. Single body means that only a single motion from the dataset is used, and multi-body means that all motions are used in the dataset. We use the Hopkins 155 dataset in order to evaluate our method, as well as some sequences that we took from for our evaluation. We can see that our method in the single body configuration performs comparably to branch and bound, which is a competing robust self-calibration method. Whereas in the multi-body case, in the multi-body settings, our method outperforms the competing robust method. An interesting point of comparison is that the vanilla Mendonça and Cipolla function produces worse results on multi-body due to the fact that multi-body the multiple motions extracted from the datasets are actually noisy and need to be handled with care when integrated in a self-calibration pipeline. Thank you very much. This was our work, multi-body self-calibration. Please reach out if you have any questions or if you would like to know more about our work. Thank you.